to have some fun this weekend. Now it's time to get back to work. Okay. So I was counting how many days we got left, and I'm trying to think. 4 days this week, 4 days next week, 1 day the week of Thanksgiving, 4 days of so we're down to our final 14 classes. T minus 14 days, 14 classes. Say what? Yeah, right. We're off Wednesday, Thursday, and Friday for Thanksgiving, right? So you have class on Monday and Tuesday. So the semester is rapidly coming to an end. We got work to do. Still. So we started covering exponential functions on Friday. And this homework is due Wednesday night. And we ended Friday graphing this function right here, right? F of x equals 2 to the minus x power. Is that what everybody has in their notes? Top of page 2. Okay. All right. So we graphed f of x equals 2 to the x and f of x equals 2 to the minus x, right? And so now we're just going to talk about what the graphs of exponential functions look like in general. And so let's actually do the one on the right first, okay? Where a is greater than 1. Okay? So we have f of x is equal to a to the x, and a is, right, the base a is a positive number greater than 1. This is like the easiest one to graph. That's why I'm doing it. So when a is a positive number greater than 1, right, the graph is going to be similar to that of f of x equals 2 to the x power, right, which we did at the bottom of page 1. So it looks something like this. For each value of a greater than 1, right, where the base is a positive number greater than 1. It's going to cross the y-axis at y equals 1. Okay, so 0.01 is the y-intercept. Okay. The domain, so down at the bottom, right, you got to write out the domain, range, the intercept, and the horizontal asymptote. Well, there's no minimum x-coordinate, right, because the graph goes to the left forever. And there's no maximum x-coordinate because it keeps going up to the right forever. And so the domain is all real numbers, minus infinity to plus infinity. The range, on the other hand, is not all real numbers, okay? Because the graph is strictly above the x-axis. Okay, so there are no negative y coordinates, and all the y coordinates are positive, right, greater than 0. I think I mentioned last Friday that the x-axis here turns out to be a horizontal asymptote. The further out you go to the left, closer the graph it gets to the x-axis without touching it. And the x-axis, right, crosses the y-axis at y equals 0. So all the y coordinates in our graph of this function are greater than 0. Okay. So the range, which is the y coordinates, goes from 0 to infinity. For every positive number greater than 0, you can find a point on the graph with that y coordinate. But there's no point on the graph with a y coordinate equal to 0. And so in inequality notation, right, we just write y is greater than 0. The intercept, I pointed out, right, crosses the y-axis at y equals 1. So you can write that as y equals 1 for the 0.01. There's obviously no x-intercept because the graph never touches the x-axis. Yes, ma'am.
Where did you get 1 at?
Where did I get what?
Yeah, the y equals 1. Where does that come from?
Well, if we evaluate the function x equals 0, we have f of 0 is equal to a to the 0, which is equal to 1. So the point 0, 1 is on the graph. Okay? So all I did was evaluate the function at x equals 0. Right? So you find the y-intercept. And then HA stands for horizontal asymptote. And as I said, the x-axis, which is the horizontal line y coincides with the horizontal line y equals 0, is the horizontal asymptote right out here on the far left. Any questions on that? Yes, ma'am.
How'd you say you got the horizontal asymptote?
Prior knowledge.
Okay.
Okay. So if you evaluate this function for large negative values of x, like we did with f of x equals 2 to the x, okay? So like a so like when we graph, so on the previous page we graphed f of x is equal to 2 to the x, right? Where a is greater than 1. If you create a table of values for x going in the negative direction, minus 10, minus 100, minus 10,000, and so forth, you see that the larger the value of x is, the more negative it is, right? The smaller this gets, the closer this gets to 0. And so as you go down, the y values get closer to 0. Right? We did a table of values in 5.1 in studying rational functions. If you do the same thing with this function, right, for an exponential function where a is greater than 1, and you create this table of values, you'll see that the large, right, the more x decreases without end, without bound, the closer the value of y gets to 0. Okay? So when x is equal to minus 10, we have like 2 to the minus 10 power, which is equal to 1 over 2 to the plus 10 power. That's already close to 0. It even gets worse as x decreases without bound. You have 2 to the minus 1,000, which is equal to 1 over 2 to the plus 1,000. Okay? And that's even closer to 0 than that number is. Okay? So you have to use your calculator. Okay? But you'll see that pattern from this table of numbers. That the farther out up to the left you go, the closer the value of the y coordinate is to 0. Okay. And that's how I knew that was a horizontal asymptote. I actually didn't put this on the board.
Okay.
All right. But those are good questions. Right? You're not treating it like magic. Any other questions on this graph? Okay. So at the top of this page, we graphed f of x equals 2 to the minus x, which we said was the same as, right at the top of the page, we graphed f of x equals 2 to the minus x, which we said was the same as 1/2 to the x power. Okay. So on the left here, we're going to graph the exponential function where the base a is between 0 and 1. And at the top of the page, what we graphed, right, a is equal to 1/2. So this graph, in general, for any base between 0 and 1, is is gonna look similar to the graph at the top of the page that we did last Friday. So now let's do the one on the left. F of x is equal to a to the x, and the base a is between 0 and 1. So, we know what the graph of fx equals 1/2 to the x power looks like. Instead of going up from left to right, it goes down from left to right. Still crosses the y-axis at point 0, 1. Okay. The domain, the range, the y-intercept, and the horizontal asymptote are the same as over here. Nothing's changed. Okay. The domain is all real numbers. The range, again, goes from 0 to infinity. The intercept again is the point 0, 1, right? Or y equals 1. And the horizontal asymptote is the horizontal line y equals 0, or the x-axis. Except the horizontal asymptote now is going to the right instead of going to the left. So remember last Friday when we graphed f of x equals 2 to the x, and then we, at the top of the page, we graphed f of x equals 2 to the minus x. We said the graph of 2 to the minus x was the graph of 2 to the x just flipped around the y-axis, right? So that's what's happening here, right? The difference between the graph when a is greater than 1 and when a is between 0 and 1/2 is that this graph over here is this graph over here just flipped around the y-axis. Okay? That one where a is greater than 1, the graph goes up from left to right. Where a is between 0 and 1, it goes down from left to right. This graph is just flipped around the y-axis from that graph over there. So any questions on that? All right, so let's take a look at example 3. We got to graph a couple of functions. So in A, we got to graph f of x equals 3 to the x plus 1 power. Okay? So we know, right, the base 3 is greater than 1, right? So the graph of f of x equals 3 to the x is going to look like this graph, similar to this graph, and cross the y-axis here at 0.01, right? But the difference is x is replaced with x plus 1, right? So we know that the graph of g of x equals 3 to the x is going to look like this graph. But we're not graphing 3 to the x, we're graphing 3 to the x plus 1. Now, do you remember when we studied transformations of functions? Right, you had a test question on that. What happens to the graph, right, when we replace x with x plus 1, what happens to the graph? It gets shifted. Which way does it get shifted? Yeah, it's left. How many units? 1. So this entire graph gets shifted to the left by 1 unit when we replace x with x plus 1. Okay? So this point here at 0, 1, when you shift it to the left 1 unit, where's that at in the coordinate plane? Is it negative 3, 1? We're shifting it to the left 1 unit. It's going to be negative 1, 1, right? And then there's going to be a new y-intercept, right? All right. So we know the graph is going to be going up from left to right, but it's going to be like this graph shifted to the left 1 unit. Okay, so it's going to go through minus 1, 1. There's 1 on the y-axis, minus 1 on the x-axis. Okay, and so since I know it's going to go up from left to right, I just evaluated the function at a couple values of x, and then I drew the curve between them. So f of minus 1 is 3 raised to the minus 1 plus 1, which is 3 to the 0, which is 1. So the point minus 1, 1 is on the graph, right, which I plotted here. And we knew that from the shift, okay? The new y-intercept, you evaluate the function x equals 0. You get 3 to the 0 plus 1, which is 3 to the first power, right, which is just 3. And so the new y-intercept is 0, 3. So here's 1, 2, 3. And so the graph is going to go up from left to right. It's going to look something like that. Here's minus 1, 1. And here's the y-intercept, 0, 3. Okay? So you got your homework, you got a lot of this going on, transformations. Now the homework you're doing multiple choice, you got like 4 graphs to choose from, right? But you can do these, you got to do this kind of deductive logic, right? Deductive reasoning, right? And getting the right graph. All right. In B, we got a graph g of x is equal to 1/4 x minus 1. Okay? So from up above, right, we know that the graph of f of x equals 1/4 to the x. Goes down from left to right and crosses the y-axis at point 0, 1. Okay? So what happens to this graph when I subtract 1 from the right-hand side? Shifts it down 1. So this entire graph is going to get shifted down 1 unit. Right? So where's the y-intercept going to be with g of x? Where's it going to cross the y-axis? At the origin, right? The y-intercept is going to get shifted down 1 unit. And the horizontal asymptote, instead of being at the horizontal line y equals 0, is going to be the what horizontal line now? Y equals -1, right? The horizontal asymptote is going to get shifted down 1 unit, right? Because the entire graph gets shifted down 1 unit. So let's graph that. Horizontal asymptote, right? And now what else are we going to have? We're also going to have an x-intercept, because this graph is going to get shifted down below the x-axis, right? It's going to cross the x-axis. So it's now going to cross The y-intercept is going to be the origin, and the horizontal asymptote is now the horizontal line y equals -1. Right? It crosses the horizontal, the y-axis at -1. Well, actually, right, the x-intercept's the origin as well, right? Yeah. So that makes life easier. We don't have to calculate that, right? So the graph is going to go down to the right. It's going to cross at the origin. It's going to flatten out to the right, right above the horizontal line y equals -1. Okay. Deductive reasoning. Okay. And you can also verify, right, that the y-intercept is the origin, because when you evaluate the function at x equals 0, you have 1/4 to the 0 minus 1, and 1/4 to the 0 power, you know, is equal to 1. The 1 minus 1, which is 0. So the 0.00 is on that. Okay. All right. All right, so any other questions on this, ladies and gentlemen? Yes, sir.
Could you quickly repeat how you figured it was -1 for the complex and so?
Because, right, the graph of fx equals 1/4 to the x, it has y equals 0 for a horizontal asymptote. And when we subtract 1 from the right-hand side of that function, it shifts everything down 1 unit. And so the entire graph gets shifted down 1 unit, which means the horizontal asymptote got shifted down 1 unit. Yes, ma'am.
What would the ranges be, -1 to infinity?
Yes, that's an excellent question. The range gets affected as well now, right? The y coordinates, right? All the y values are greater, strictly greater than -1, right? The range is -1 to infinity. Yep. Yep. Excellent question. Yep. All right. Any other questions on these two graphs? All right, so you flip over to page 3. We're going to learn about a very special exponential function called the natural exponential function. How many of you worked with the number e in high school? That's somebody's word, right? You worked with the number I, square root of -1. Worked with pi, 3.141. And now we have a third number with its own name. It's the number e. And where on earth did that come from? So, I have this sequence of numbers. 1 plus 1 over n to the n. Okay? Any of you work with sequences of numbers in high school? Right? I can remember way back in the olden days, right? We worked with sequences of numbers. And so it's like creating a table of values. In the first column goes n, right? N is the nth represents the nth number in the sequence. And the value of the number, of the nth number in the sequence is 1 plus 1 over n to the n, right? So you start off at n equals 1, then n equals 2, 3, 4, 5, 6, 7, 8, 9, 10, on and on forever, okay? to get the sequence of numbers in this sequence. So when you put 1 in for n, you have 1 plus 1 over 1, which is 2. 2 to the first power is 2. So the first number in the sequence is 2. The second number, n is the index, I should say, is the index in the sequence of numbers, right? So n equals 2, right? Second number in the sequence, you put 2 in for n up here, and you have 1 plus 1/2 squared, which is equal to 2.25, right? So that's the second number in the sequence. Now we jump down to n equals 10, right? The 10th number in the sequence. You put 10 in for n, you have 1 plus 1/10 to the 10th power, and you get 2.59. Right? Get the idea? And so you go down to the 100th number in the sequence. N equals 100. You put 100 in for n. And the value of that number, the 100th number in the sequence, is 2.70. And you can see that the values of n, right, are starting to get large, but the numbers in the sequence aren't changing that much. And so you go all the way up to like 10,000, the 10,000th number in the sequence. Put in 10,000 in for n. The value of the 10,000th number in the sequence is 2.718. Just 3 decimal places. Okay. And what happens, we say in mathematics, is n is increasing without end, without bound. The numbers in the sequence are converging. The sequence of numbers converging to a specific number on the real number line. And that specific number on the real number line is 2.71828 to 5 decimal places. And so they gave this special number, which is, right, the number that our sequence converges to, a special name. They called it E. Okay? They gave its own letter of the alphabet. So E equals 2.71828 to 5 decimal places, right, is what this sequence of numbers on the right-hand side converges to as n increases without end, without bound. Okay? Special number. Okay? Well, E is a positive number greater than 1. So we can replace A with E in the definition of exponential functions. Our definition of an exponential function is f of x is equal to a to the x, and a has to be a positive number greater than 1. E is a positive number greater than 1, so we replace a with E, we have f of x is equal to e to the x. Okay. And that is called the natural exponential function. And the number E comes from this sequence of numbers over here. Okay? They just didn't make it up. So in example 4, we got a graph f of x equals e to the x. Well, e is greater than 1. So it's graphed from what we've already done, okay? On the previous page, its graph is going to go up from left to right. and it crosses the y-axis at the point 0, 1. Just like on page 2. Okay. And so you can verify it crosses the y-axis at the point 0, 1, because when you evaluate this function x equals 0, you get f of 0 is equal to e to the 0, and e to the 0 is equal to 1. Any non-zero number raised to the 0 power, is equal to 1. In B, we got a graph g of x is equal to e to the minus x minus 1 power. And to graph this, right, you can perform a series of transformations on this function, right? Or you can just plot a few points and play connect the dots, okay? So, if you evaluate this function x equals 1, we have g of 1 is equal to e to the minus 1 minus 1 power. 1 minus 1 is 0, minus 0, 0, so we have e to the 0, which is 1. So the point 1, 1 is on the graph. So here's x equals 1, here's y equals 1, there's the point 1, 1. Now to find a y-intercept, we evaluate the function x equals 0. We have g of 0 is equal to e to the minus 0 minus 1 power. 0 minus 1 is negative 1. Negative 1 is plus 1. So this e to the first is just e. So the point 0e to the first power is the y-intercept. Well, what's the value of e? 2.71, right? So e is less than 3, but greater than 2, right? It's roughly 2 3/4. So there's e on the y-axis, okay? And so the graph crosses the y-axis here, goes through this point, so you can deduce the graph is going to go down and to the right. The y-intercept is 0e, and it goes through the point 1, 1. There was no vertical, you can tell there's no vertical shift, because there's nothing added or subtracted from the right-hand side of the function e to the x, okay? Any questions on that? Okay. Let's look at example 5, which is a word problem. Chlorine is frequently used to disinfect swimming pools. The chlorine concentration should remain between 1.5 and 2.5 parts per million. On warm sunny days with many swimmers agitating the water, 30% of the chlorine can dissipate into the air combined with other chemicals. So we have this mathematical model. F of x equals 2.5 times 0.7 to the x model the amount of chlorine in a pool after x days. What is the initial concentration of chlorine in the pool? F of x is equal to 2.5 times 0.7 to the x power, okay? That tells us how much chlorine is in the pool after x days, okay? to find the initial concentration. Initial concentration is that x equals 0, right? X is time. So we have f of 0 is equal to 2.5 times 0.7 to the 0 power. Now remember, you gotta follow the arithmetic, you gotta follow order of operations, right? Exponentiation comes before multiplication. You don't multiply 2.5 times 0.7. You take 0.7 to the 0 power first. Well, 0.7 to the 0 power is equal to 1. So we just have 2.5 times 1, which is 2.5. So the initial concentration ends up being this multiplicative constant. But what are the units?
Parts per million, right?
Yeah, parts per million. Units are important in word problems. So that's the initial amount of chlorine. In B, it says if no chlorine is added, estimate the number of days before chlorine should be added. Well, the amount of chlorine needs to remain between 1.5 and 2.5. So they got to add chlorine when the amount of chlorine parts per million gets down to 1.5, right? When the amount of chlorine gets down to 1.5 parts per million. So to find out how many days until it gets down to 1.5 parts per million, we replace f of x on the left-hand side with 1.5, and then we got to solve for x. That'll give us the number of days until the chlorine decreases to 1.5 parts per million. So we set the right-hand side, 2.5 times 0.7 to the x equal to 1.5, and then we got to solve for x to see how many days it takes for the chlorine to get down to 1.5 parts per million. So, you know, we divide both sides. By 1.5, or 2.5, excuse me. You know, division undoes multiplication. 2.5's cancel on the left, and we're left with 0.7 to the x power is equal to 0.6. You'll need your calculator, okay, in solving this problem. Now, in 5.2, the solution to this equation involves a logarithm. But we're not there yet, right? So how do we solve for x without the logarithm? Trial and error. And so by trial and error, I got x is approximately equal to, that's what that means. Doesn't mean even, it's approximately equal to 1.4 days. So after 1.4 days, chlorine will decrease to 1.5 parts per million, and they'll have to add more chlorine. Okay. Trial and error. All right. Any questions? All right, so let's take a look at example 6. And start to find an exponential function f of x equals b dx, such that the graph of f passes through the point 2,9. of x is equal to b of the x, I'm sorry. So what it's asking is, you know, what is b? Now, x is the variable, right? We gotta find the value of b so that the graph of this function goes through the point 2, 9. You know, 2 is the x coordinate, 9 is the y coordinate. Okay? So we replace, remember, function values and y values are the same. So we replace f of x with y. And now we use that point to find b. Y is equal to 9. X is equal to 2. And now we solve for b. So we switch the two sides, we get b squared is equal to 9. In an exponential function, can the base be negative? A definition of exponential function is the base is greater than is a positive number greater than 0, right? So we can only take the positive square root of both sides. Can't take the negative. And so we get b is equal to plus 3 when we take the square root of both sides. And so now we replace b and f of x with 3. We have f of x is equal to 3 to the x power. So this exponential function passes, this graph passes through that point in the coordinate plane. Okay. Any questions on that? Yes, ma'am.
When you did the square root, how did you know it wasn't like -3?
Because the base, the definition of an exponential function, a to the x,
Oh, okay.
right?
Yeah.
A has to be
Greater than-
greater than 0. Okay? That's why I said you can't take the negative square root. Okay? All right, any other questions? All right, so you flip over to page 4. We have the one-to-one property of exponential functions. So we'll demonstrate that with the first example on the left. We have 27 raised to the x minus 1 power is equal to 9 to the 2x minus 3 power. Okay. All right. Well, we can't just equate these two exponents to each other because the base, the exponential on the left, is the different base of the exponential on the right. But if you look closely, 27 is equal to 3 cubed. So I'm going to replace 27 with 3 cubed. And 9 on the right is equal to 3 squared. So I'm going to replace it with 3 squared. Okay. And now by the rules of exponents, 3 cubed raised to x minus 1, you multiply the exponents when you simplify, right? So we have 3 raised to 3 times x minus 1 power. And on the right, you simplify, you multiply the exponents, you get 2 times 2x minus 3. Now we have an exponential on the left and an exponential on the right with the same base. And so the one-to-one property of exponential function says I can now equate those two exponents and solve for x. So we have 3 times x minus 1 is equal to 2 times 2x minus 3. So when I distribute the 3 on the left hand side, I have 3x minus 3. And when I distribute the 2 on the right hand side, I have 4x minus 6. So now I can subtract 4x from both sides and add 3 to both sides. When I do that, I get minus x on the left is equal to minus 3 on the right. Now when I divide both sides by -1, I get x is equal to 3. So you put 3 in for x over here, you end up with 27 squared is equal to 9 to the 3rd power. You can verify that the left-hand side equals the right-hand side using your calculator. Okay? Alright, so you have more than enough to do the homework that's due Wednesday night, okay? So I'll see you in class on Wednesday.